Something just happened out there as it passes through our inner solar system, and it defies every prediction we had. The coma surrounding interstellar comet 3I Atlas has expanded by 44% in a time frame that is unusual and challenges current cometary models. This isn't a gradual change or a subtle shift that takes months to detect. This is a rapid expansion that surprised astronomers who have been watching this visitor from another star system since it entered our cosmic neighbourhood. And here's what raises eyebrows. The thermal readings coming back from deep space observatories don't match anything we've ever recorded from a comet, local or interstellar. The heat signatures are unusual. The patterns differ from expectations. The distribution challenges current models. We're looking at data that suggests something not yet fully understood is happening inside this object. Something that challenges our understanding of how frozen bodies from alien star systems behave when they encounter our Sun. Right now, as you're watching this, telescopes around the world are pointed at this enigmatic traveller, trying to make sense of readings that seem to break the rules. Scientists who have spent decades studying comets are scratching their heads, revisiting their models, and asking questions they never thought they'd need to ask. What could cause a coma to balloon outward with such unprecedented speed? What kind of internal processes generate thermal patterns that look nothing like the comets we've observed for centuries? And perhaps the most unsettling question of all, what does this tell us about the star system this comet came from and the physics that govern objects born in the cold void between stars? Stay with me, because in the next several minutes we're going to dive deep into the most mysterious cosmic visitor humanity has tracked in modern history, explore the baffling expansion that has astronomers worldwide talking in urgent tones, examine thermal data that reads like science fiction, and confront the very real possibility that 3I Atlas is showing us something we've never seen before. Something that might rewrite what we think we know about interstellar objects. This isn't just another comet story. This is a front-row seat to a cosmic mystery unfolding in real time, and the implications reach far beyond a single icy wanderer. When an object from another star system enters ours and starts behaving in ways that violate our expectations, it forces us to confront a humbling truth. The universe is stranger, more complex, and more diverse than our earthbound observations have prepared us for. Every assumption we've made about how matter behaves in deep space, how frozen volatiles respond to solar radiation, how objects formed in alien stellar environments differ from those born in our own system. All of it is being tested right now by this enigmatic visitor. The Coma expansion isn't just large, it's staggeringly larger than typical for the time frame we're talking about. Imagine watching a cloud grow by nearly half again its size over days, instead of drifting and changing slowly over hours. That's the cosmic equivalent of what we're witnessing. The gas and dust envelope surrounding the nucleus of 3I Atlas has swelled to dimensions larger than typical models predicted given the comet's distance from the Sun, its velocity, its trajectory, and every model we've built based on decades of observing cometary behaviour. And this expansion isn't chaotic or random. There's a structure to it, a symmetry that suggests organised processes at work, not just the typical outgassing you'd expect from a chunk of ice warming up as it approaches a star. But the real story, the part that has scientists staying up late reviewing data and running simulations, is in the thermal readings. Heat maps captured by infrared observations show patterns that simply don't align with normal cometary activity. When a typical comet approaches the Sun, we know exactly what to expect. The side facing the Sun heats up, volatiles sublimate, jets of gas and dust shoot outward, creating the characteristic tail, and the thermal signature follows predictable patterns based on rotation, composition, and solar distance. What we're seeing with 3I Atlas doesn't follow that script. The heat distribution is unusual, concentrated in regions that shouldn't be the warmest, varying in ways that suggest something more than simple solar heating is at play. This is the kind of discovery that changes careers, the kind of data that gets published in major journals and debated at conferences for years to come. But it's also the kind of mystery that reminds us how little we truly understand about the broader universe beyond our solar backyard. We've observed thousands of comets, studied their compositions, tracked their orbits, predicted their behaviour with remarkable accuracy. But 3I Atlas, this visitor from the vast space between stars, is playing by different rules, and we're scrambling to understand why. So before we go any further, I need you to do something for me. If this mystery grips you the way it grips the scientists tracking this comet, If you want to be part of the conversation as this story unfolds, hit that like button right now. Let me know you're here, that you're ready to explore this cosmic enigma together. Drop a comment and tell me what you think could explain this expansion. Are we missing something fundamental about interstellar comets? Is there a process happening inside 3I Atlas that we've never encountered before? Your thoughts matter, and this community thrives when we share ideas, ask questions, and wonder together about the universe's deepest mysteries. And make sure you're subscribed with notifications on, because as new data comes in, as scientists piece together more of this puzzle, we'll be here breaking it down, exploring every angle, and following this story wherever it leads. Now let's talk about what we're actually seeing, because the images coming back from observatories are as stunning as they are perplexing, and they're forcing us to ask questions we never anticipated. When the latest images of 3I Atlas started circulating among the astronomical community, the reaction was immediate and intense. These weren't incremental updates showing gradual changes over weeks or months. These were dramatic before and after comparisons that showed a transformation so rapid and so pronounced that initial reports were met with skepticism until multiple independent observations confirmed what seemed highly unusual. The Coma, that diffuse envelope of gas and dust that surrounds the solid nucleus, had expanded outward in a symmetric pattern, more isotropic than expected. Look at any textbook image of a comet, and you'll see a predictable structure. The nucleus, a relatively small solid body made of ice, rock, and organic compounds. The Coma, a cloud surrounding the nucleus formed as solar heat causes surface ice to sublimate. And the tail, that iconic streamer of material pushed away by solar wind and radiation pressure. The shape, size, and evolution of these features follow well understood physics. We can predict how a coma will grow as a comet approaches the Sun, how it will shrink as the comet recedes, how it will respond to changes in solar radiation and the comet's rotation. We've been doing these calculations for generations, and they work. Until they don't. The images of 3I Atlas show something fundamentally different. The Coma isn't just larger than it should be for the comet's current position and activity level. It's expanded in a way that suggests an internal event, a sudden release of material that overwhelmed the typical steady-state outgassing we expect from comets. And here's what makes it truly bizarre. The expansion is remarkably uniform, creating a structure more isotropic than typical comets around the nucleus, rather than the asymmetrical jet-driven structures we normally observe. This uniformity suggests that whatever is driving the expansion isn't coming from localized active regions on the surface responding to solar heating. It's something more global, more comprehensive, as if the entire nucleus suddenly became active at once. Think about what that means from a physical standpoint. Comets are not uniform objects. They have varied compositions across their surfaces, different concentrations of volatiles, regions that are more active than others based on exposure to sunlight and internal structure. When a comet heats up, you get jets, discrete streams of material shooting out from specific locations, creating irregular coma structures and sometimes leading to dramatic outbursts from particularly active regions. What you don't typically get is a smooth, symmetric expansion unless something is driving activity uniformly across the entire object, and that's exactly what these images suggest is happening with 3I Atlas. Several research teams immediately began analyzing the morphology of this expanded coma, looking for clues about what could drive such unusual behavior. The symmetry alone is a puzzle worth solving. In planetary science and cometary studies, symmetry often points to underlying physical processes that are either extremely well organized or operating on scales large enough to smooth out local variations. For a coma to expand uniformly in all directions suggests that the driving force isn't localized solar heating, which would naturally create asymmetry as the sun-facing side receives more energy than the shadowed side. Instead, it suggests an internal energy source or a composition so volatile that even modest solar heating triggers widespread activity. But there's another possibility that some researchers are beginning to explore, and it's one that pushes us into less familiar territory. What if the nucleus of 3I Atlas has a structure or composition unlike anything we've encountered in solar system comets? Objects born in other stellar environments might incorporate volatiles with different freezing points, different mixing ratios, different mechanical properties. They might have experienced formation conditions, radiation environments, or chemical processes that don't occur in our solar neighbourhood? If that's the case, then our models, built entirely on observations of local comets, might simply not apply. We might be trying to predict the behaviour of an apple using equations derived from studying oranges. The images also reveal something else that's capturing attention. The edges of the expanded coma aren't sharp. There's no clear boundary between the dense inner region and the more diffuse outer regions, which you might expect if this were a discrete outburst event. Instead, there's a gradual transition, a smooth gradient that suggests ongoing activity rather than a single explosive release. This points to a sustained process, something that's continuously feeding material into the coma and maintaining its expanded state. That kind of sustained activity requires either an abundant reservoir of volatiles near the surface, or an internal mechanism that's efficiently transporting material from deeper regions to the surface where it can sublimate and escape. Now here's where the story gets even more intriguing. When astronomers compare the visible light images showing the expanded coma with images taken at different wavelengths, particularly in the ultraviolet and near-infrared, they find discrepancies that hint at compositional complexity. Different wavelengths reveal different chemical species within the coma. Some wavelengths show strong emission from water vapour, others from carbon monoxide, others from more exotic species like cyanogen compounds or diatomic carbon. The relative abundances and spatial distributions of these species don't quite match what we expect from solar system comets, suggesting again that 3I Atlas carries with it the chemical fingerprint of its alien birthplace. What makes these new images truly shocking to the scientific community isn't just that they show something unexpected, it's that they show something unexpected happening to an object that was already extraordinary by virtue of its interstellar origin. We've only detected a handful of confirmed interstellar objects passing through our solar system. Each one is precious, a rare opportunity to study matter formed around another star, to glimpse the diversity of planetary system formation processes, to test whether our theories of comet physics apply beyond our local environment. When one of these rare visitors starts behaving in ways that challenge those theories, it's both exciting and unsettling. Exciting because we're learning something genuinely new. Unsettling because it reveals how much we still don't know. The astronomical community is responding with urgency. Observing time on major telescopes is being redirected toward 3I Atlas. Researchers who study comets, planetary atmospheres, and interstellar chemistry are collaborating, pooling expertise to make sense of the data. There's a race against time because interstellar objects don't linger. They pass through our solar system once, on hyperbolic trajectories that will carry them back into the void between stars, never to return. Every day of observation is precious. Every image, every spectrum, every measurement adds another piece to a puzzle we might never get another chance to solve. And as more images come in, as monitoring continues and the expanded coma evolves, one thing becomes crystal clear. This isn't a simple story of a comet warming up and releasing gas. This is something more complex, something that's pushing our understanding and demanding better models, better theories, better questions. The images are beautiful, haunting even, but they're also deeply challenging to everything we thought we understood about how frozen bodies from deep space behave when they encounter a star's warmth. And if the images are shocking, wait until you see what the thermal data reveals, because that's where this mystery takes a turn from puzzling to genuinely unnerving. When infrared telescopes turned their sensors toward 3I Atlas to map the thermal signature of this expanding enigma, they expected to see patterns consistent with standard cometary activity. What they got instead was data that prompted urgent follow-up observations and sent research teams scrambling for explanations. The heat distribution across the coma and nucleus doesn't match any template in the cometary physics playbook. The thermal maps show hotspots, temperature gradients, and energy distributions that suggest processes we don't fully understand are unfolding inside this interstellar visitor. Let's establish what normal looks like first, because that context makes the anomalies all the more striking. When a typical comet approaches the Sun, thermal mapping is straightforward and predictable. The sun-facing hemisphere heats up significantly, sometimes reaching temperatures high enough to sublimate water ice, and even more volatile compounds like carbon dioxide and carbon monoxide. The night side, shielded from direct solar radiation, remains much colder, often barely above the background temperature of deep space. This creates a strong thermal gradient from day to night side, and as the comet rotates, You can track the heating and cooling cycle. Jets of sublimating gas cool their immediate surroundings through the physics of phase change, creating localized cold spots. Meanwhile, areas with darker, less reflective material absorb more sunlight and become thermal hotspots. All of this is well understood, measurable, and predictable. Now look at the thermal maps of 3I Atlas, and you immediately see that something is off. The temperature distribution doesn't show the expected strong day-night asymmetry. Instead, there are regions of elevated temperature in areas that should be relatively cool based on solar illumination alone. The hotspots don't correlate neatly with the locations of visible jets or the orientation toward the sun. Some of the warmest regions appear to be on portions of the nucleus that shouldn't be receiving direct solar heating, at least not intense enough to explain the observed temperatures. This suggests that internal heat transport, subsurface structure, or compositional variations are playing a significant role, perhaps a dominant role, in determining where and how heat manifests on this object. Even more puzzling is the overall thermal signature of the expanded coma itself. Gas and dust released from the nucleus should cool rapidly as it expands into space. That's basic thermodynamics. As material moves outward from the nucleus, it spreads into a larger volume, density drops, and without a continuous energy input, temperature plummets. The thermal maps should show a hot nucleus surrounded by progressively cooler material as you move outward through the coma. What we're seeing with 3I Atlas doesn't quite follow that pattern. There are regions within the expanded coma that retain heat better than expected, suggesting either that the particle density is higher than visual observations would indicate, that the material has unusual thermal properties, or that there's some ongoing process within the coma that's generating or retaining heat. Now, I need to be clear here, because this is where speculation starts creeping into public discussions, and it's important to separate what the data actually shows from what people are theorizing it might mean. The raw data, the actual thermal measurements, show anomalies. They show temperatures and distributions that don't match standard models. What they don't show, at least not unequivocally, is the cause of those anomalies. Various hypotheses are being discussed, ranging from perfectly reasonable explanations rooted in known physics, to more speculative ideas that invoke exotic processes. The scientific method requires that we don't jump to conclusions, that we test hypotheses rigorously, and that we remain open to mundane explanations even when the data seems strange. That said, the thermal anomalies are real, and they're significant enough that they can't be dismissed as measurement errors or artifacts. Multiple independent observations using different instruments and techniques have confirmed the basic findings. The heat patterns are genuinely unusual, so what could explain them? One possibility that's gaining traction among researchers is that the rotation of 3I Atlas is not what we initially assumed. Most comets rotate relatively regularly, though often with complex spin states that involve wobbling or tumbling. If 3I Atlas has a particularly irregular rotation, or if it's tumbling chaotically, that could create thermal patterns that don't match simple models assuming uniform rotation. Irregular rotation means different parts of the surface receive vastly different amounts of solar heating over time, leading to complex thermal maps that can appear anomalous if you don't account for the true spin state. Another intriguing possibility involves the internal structure of the nucleus. We tend to think of comets as relatively homogeneous, dirty snowballs, but that's an oversimplification. Comets can have complex internal structures, with layers of different compositions, voids and cavities, regions where volatiles are concentrated versus regions that are more rocky and refractory. If 3I Atlas has a particularly complex interior, with pathways that allow heat to be transported from the sun-warmed surface to deeper layers, or with subsurface pockets of volatiles that are sublimating and releasing energy, that could create surface thermal patterns that don't correlate simply with solar illumination. It's like trying to predict the temperature distribution on a house based only on where the sun hits the roof, ignoring the heating system inside. There's also the possibility, and this is where things get particularly interesting, that we're possibly seeing signs consistent with cryovolcanic activity. Cryovolcanism, the eruption of volatiles and icy materials from beneath the surface, is known to occur on some moons in the outer solar system. Enceladus and Europa, for example, have active plumes that shoot water and other materials into space from subsurface oceans. These plumes are driven by internal heat, tidal forces, and pressure buildup. While we don't expect tidal forces to play a role in a solitary comet far from any massive body, Internal heat from radioactive decay or from the energy released during crystallization of amorphous ice could potentially drive similar processes. If 3I Atlas has regions where subsurface volatiles are under pressure and finding pathways to the surface that could create thermal signatures that look very different from standard solar-driven sublimation. But here's the critical point that needs emphasis. While cryovolcanism is a fascinating possibility, and while it could explain some of the observations, there's no definitive evidence yet that this is what's happening. The thermal data is consistent with cryovolcanic activity, but it's also potentially consistent with other explanations. Science progresses by eliminating hypotheses that don't fit the data, and by designing observations that can distinguish between competing theories. Right now, we're in the hypothesis generation phase, where researchers are identifying all plausible explanations and beginning the process of testing them against additional observations. The thermal readings also raise questions about the composition of 3I Atlas's nucleus. Different materials have different thermal properties. They absorb and emit heat at different rates, they conduct heat through their structures with different efficiencies, and they respond to solar radiation in distinct ways. If the nucleus of 3I Atlas contains materials or mixtures that are rare or absent in solar system comets, that could contribute to the unusual thermal signature. We know from spectroscopic studies that interstellar chemistry can produce compounds that are uncommon in our local environment. It's entirely possible that this visitor carries with it ices and minerals that formed under conditions we can't replicate in our models because those conditions don't exist in our solar neighborhood. What makes the thermal data particularly unnerving, to use the word deliberately, isn't that it's ambiguous or unclear, it's that it's too clear. The signatures are strong, the anomalies are pronounced, and they're consistent across multiple observations. This isn't a marginal effect that might disappear with better data. This is a robust signal telling us that something different is happening, and our current understanding isn't sufficient to fully explain it. That combination of clear data pointing to unclear processes is what drives scientists forward, but it's also what keeps them up at night wondering what they're missing. What crucial piece of the puzzle hasn't been recognized yet? As thermal monitoring continues, as more detailed maps are created and compared across different observing sessions, researchers hope to see patterns emerge that will narrow down the possibilities. Is there a correlation between thermal hotspots and compositional variations detected spectroscopically? Do the thermal patterns change with rotation, or are they stable over time? Are there temporal correlations between thermal spikes and changes in the visible Coma structure? Each of these questions can be answered with sustained observation, and each answer will help discriminate between competing hypotheses. But right now, in this moment, we're left with heat maps that challenge our understanding and force us to confront the possibility that interstellar comets are not just distant cousins of our local comets, but genuinely different beasts with behaviors and properties we're only beginning to discover. And if the thermal maps are confusing, the question of what's driving them becomes even more complex when we consider the possibility that rotation itself might be part of the mystery. The question of how 3I Atlas is rotating might seem like a technical detail, something only specialists care about, but it's actually central to unraveling the mystery of the Coma expansion and thermal anomalies. Rotation affects everything about how a comet behaves. It determines which parts of the surface are exposed to sunlight and for how long. It influences where jets of sublimating gas emerge and in what directions they push. It shapes the overall thermal environment of the nucleus and affects how heat is distributed. And in the case of 3I Atlas, rotation or the lack of a simple rotation may be the key to understanding why this comet is behaving so strangely. When astronomers first started tracking 3I Atlas, they attempted to determine its rotation period using standard photometric techniques. By monitoring how the brightness of the nucleus changes over time, you can usually infer the rotation period, because as different regions of the surface rotate into and out of view, the total amount of light reflected varies. For many comets, this technique works beautifully, revealing rotation periods ranging from a few hours to a few days. For 3I Atlas, the results have been frustratingly ambiguous. The light curve, the plot of brightness versus time, doesn't show the clear periodic signal you'd expect from a nicely rotating object. Instead, it shows complex variations that suggest either a very irregular shape, a tumbling rotation state, or possibly even a binary system where two objects are orbiting each other. Why does this matter for the thermal and Coma observations? because rotation state directly impacts how solar energy is deposited on the surface and how that energy drives activity. A comet in a simple rotation, spinning around a single axis like a top, will have predictable patterns of heating. You can calculate which regions see the sun, for how long, and how much energy they absorb. From that, you can predict where sublimation will be strongest, where jets should form, and what the thermal map should look like. But if the comet is tumbling, if it's rotating in a complex way that involves precession or nutation, then those predictions become much harder. Different parts of the surface receive solar energy in non-intuitive patterns, and the thermal response becomes correspondingly complex. There's some evidence, though not yet conclusive, that 3I Atlas might be in what's called an excited rotational state. This means it's not just spinning smoothly, but tumbling end over end or wobbling as it spins. This kind of rotation typically happens when an object experiences a sudden change in mass distribution, or when outgassing jets create torques that alter the spin. For a comet that's actively outgassing, especially one experiencing the kind of dramatic expansion we're seeing with 3I Atlas, those torques can be significant. Jets shooting off from the surface carry momentum, and by Newton's third law, they exert forces on the nucleus that can change how it rotates. If the outgassing is asymmetric, if certain regions are far more active than others, the resulting torques can spin the comet up, slow it down, or send it into a tumble. Now imagine trying to interpret thermal maps and coma structures for an object that's tumbling chaotically. Every observation captures the comet in a different orientation, with different parts of the surface exposed to view and to the sun. What might look like anomalous heating in one observation could simply be a particularly dark or volatile-rich region that happened to be facing the sun at that moment. Without knowing the precise rotation state and three-dimensional shape of the nucleus, it's incredibly difficult to disentangle what's truly anomalous from what's just a consequence of complex rotation. This is one of the major challenges researchers are grappling with right now. They need to determine the rotation state to make sense of the thermal data, but they need good thermal and coma data to infer the rotation state. It's a classic problem in astrophysics, where multiple variables are coupled, and you have to solve for them simultaneously. But there's another possibility that some researchers are beginning to seriously consider, and it's one that takes us into territory that's less well explored in cometary science. What if the activity driving the coma expansion isn't primarily controlled by rotation and solar heating at all? What if there's an internal process, something happening beneath the surface, that's driving out gassing in a way that's relatively independent of where the sun is shining? This is where the idea of cryovolcanism resurfaces, but now framed in terms of its potential to decouple cometary activity from simple solar heating. Cryovolcanism, in the context of icy bodies, involves the eruption of volatile materials from beneath the surface, driven by internal pressure or heat sources rather than direct solar illumination. We see this clearly on moons like Enceladus, where plumes emerge from the south polar region continuously, driven not by sunlight, which varies as the moon orbits Saturn, but by tidal heating and internal structure. If something analogous is happening with 3I Atlas, if there are subsurface reservoirs of volatiles that are reaching critical pressures, or that are being heated by internal sources, then outgassing could occur relatively uniformly across the surface, or from discrete vents that aren't tied to the sun-facing side. This would produce exactly the kind of symmetric coma expansion and unusual thermal patterns that we're observing. Of course, the question then becomes, what could heat the interior of an interstellar comet? Tidal heating, the mechanism that powers Enceladus's activity, doesn't apply to a solitary object far from any massive body. Solar heating penetrates only millimeters to centimeters into the surface of a comet, not deep enough to affect the interior unless there's active heat transport. One possibility is residual heat from the comet's formation. Objects that form in protoplanetary disks can start out relatively warm, and if they're large enough and insulating enough, they can retain some of that heat for millions of years. Another possibility is radioactive decay. While most comets are too small and contain too little radioactive material for decay heating to be significant, we don't know the exact size or composition of 3I Atlas's nucleus. If it's larger than typical comets, or if it has an unusual concentration of radioactive isotopes, decay heating could contribute to internal temperatures. There's also the intriguing possibility that exothermic chemical reactions or phase transitions are occurring within the nucleus. Amorphous ice, which can form in the extreme cold of interstellar space, releases energy when it crystallizes into regular ice. This phase transition happens at specific temperatures and can release enough heat to trigger further sublimation of volatiles. If 3I Atlas contains significant amounts of amorphous ice that's now crystallizing as the comet warms slightly in its passage through the inner solar system, that could provide an internal heat source that drives activity from within. This process can be somewhat self-sustaining. Crystallization releases heat, which warms neighboring material, which triggers more crystallization, creating a runaway effect that could explain sudden increases in activity like the Coma expansion we're witnessing. The challenge is that distinguishing between these possibilities requires data we don't yet have. We need better constraints on the rotation state, which requires extensive photometric monitoring and possibly radar observations if the comet comes close enough. We need detailed compositional analysis to understand what volatiles are present and in what abundances, which requires high-resolution spectroscopy. We need thermal modeling that accounts for complex surface and subsurface structures, which requires assumptions about properties we can only guess at. Each piece of information helps narrow the possibilities, but right now the solution space is still uncomfortably large. What's particularly fascinating from a scientific standpoint is that this ambiguity, this uncertainty about whether we're seeing rotation-driven phenomena or something more exotic, is exactly the kind of problem that drives scientific progress. It forces researchers to think carefully about assumptions, to design clever observations that can break degeneracies between competing models, and to collaborate across disciplines. Experts in cometary physics are talking to specialists in icy moon geology, to planetary scientists who study rotation dynamics, to astrochemists who understand how materials behave at extreme temperatures. This cross-pollination of ideas often leads to breakthroughs that wouldn't happen if everyone stayed in their lanes. And there's something deeply human about this moment of uncertainty. We're confronted with a cosmic mystery that resists easy explanation, and our response is to bring together our best minds, our best instruments, and our best theories to crack it. We're driven not by practical concerns or immediate applications, but by pure curiosity, by the fundamental human need to understand the universe around us. The rotation of 3I Atlas matters not because it affects our daily lives, but because it's a puzzle, and we're a species that can't resist puzzles. That drive, that curiosity, is what's pushing us forward as new data comes in and as the mystery deepens with every observation. And speaking of deepening mysteries, there's another layer to this story that adds even more intrigue. The fact that this enigmatic object doesn't come from our solar system at all, and that alien origin might be the single most important factor in understanding its bizarre behavior. There's something profoundly significant about the fact that 3I Atlas is an interstellar visitor, and it's not just the romantic notion of studying an object from another star system, though that alone is enough to quicken the pulse of anyone interested in space. The interstellar origin means this comet formed in a completely different environment, under different conditions, from different materials than any of the thousands of comets we've studied that call our solar system home. And that difference, that alien provenance, might be the key to understanding why its behavior is so puzzling, why our models built on local observations don't quite fit, why the Coma expansion and thermal readings defy our expectations. Think about what it means for an object to form around a different star. The chemical composition of the protoplanetary disk, the cloud of gas and dust from which planets and comets form, depends on the star's properties and its local galactic environment. Stars of different masses, ages, and metallicities produce different ratios of elements through nuclear fusion and supernova processes. The interstellar medium from which stars and their disks form varies in composition from one region of the galaxy to another. All of this means that the raw ingredients available for building comets around another star might be significantly different from what was available in the early solar system. We know from spectroscopic studies of interstellar space that the chemistry out there is rich and complex. Molecules that are rare or short-lived in our solar system can be abundant in the cold, radiation-rich environment of the interstellar medium. Complex organic compounds, exotic ices formed at temperatures near absolute zero, mixtures of volatiles with unusual ratios, all of these could be incorporated into objects forming in other stellar systems. When 3I Atlas formed, it likely incorporated materials that reflect the specific chemistry of its birth environment, and those materials might behave very differently from the water ice, carbon dioxide, and methane that dominate solar system comets. This compositional difference has profound implications for how the comet responds to solar heating. Different ices sublimate at different temperatures. Water ice requires relatively warm conditions, carbon dioxide sublimates at much colder temperatures, and other volatiles like carbon monoxide or nitrogen ice are even more easily vaporized. If 3I Atlas has a composition dominated by highly volatile species that are less common in solar system comets, then even modest solar heating could trigger vigorous outgassing. This could explain the dramatic Coma expansion. The comet might be more responsive to solar energy than our models predict, because it contains ices that sublimate more readily than we're accustomed to. But composition is just one aspect of the interstellar difference. There's also the matter of structure and formation history. Comets in our solar system formed relatively quickly after the birth of the Sun, incorporating materials from the solar nebula before it was dispersed. They spent billions of years in the cold storage of the Oort cloud or Kuiper belt, occasionally perturbed into orbits that bring them into the inner solar system. During that long storage, they experienced cosmic ray bombardment, occasional impacts, and slow thermal evolution driven by radioactive decay and solar irradiation. All of these processes shape the structure, porosity, and layering of cometary nuclei. 3I Atlas has a completely different history. It formed around another star, then was somehow ejected from its birth system and sent wandering through interstellar space. That ejection process itself could have been violent, potentially involving close encounters with planets or other massive bodies that imparted enough energy to fling the comet out of its system entirely. Such encounters could have fractured the nucleus, created internal cracks and voids, or even stripped away outer layers. Then, during its journey through interstellar space, potentially lasting millions or even billions of years, 3I Atlas was exposed to the interstellar radiation environment, to cosmic rays unshielded by any star's magnetic field, to temperatures near absolute zero. These conditions could have altered the structure of ices within the nucleus, created amorphous phases that don't exist in warmer environments, or driven chemical reactions that produced exotic compounds. All of this history, all of this alien experience, is encoded in the comet's current structure and composition. When we observe 3I Atlas, we're not just seeing a frozen chunk of ice and rock. We're seeing the physical record of another planetary system's formation, of an ejection event that sent this object into the void, of millions of years drifting through the space between stars. Every anomaly we detect, every deviation from expected behavior, is potentially a clue to that history. The Coma expansion might be telling us something about the volatility and structure of materials formed in a different stellar environment. The thermal anomalies might be revealing internal structures created by that long interstellar journey or by the violent ejection from its home system. There's also a psychological dimension to the interstellar difference that's worth acknowledging. When we study solar system comets, we're studying objects that are, in a sense, part of our cosmic family. They formed from the same cloud of gas and dust that gave birth to the Sun, to Earth, to everything familiar in our neighbourhood. There's a comfort in that familiarity, an assumption that we understand the fundamental processes at work, because they're the processes that created our world. But 3I Atlas is a stranger. It comes from elsewhere, formed under unknown conditions, shaped by forces and events we didn't witness and can't directly study. That strangeness challenges our assumptions and forces us to confront the diversity of cosmic processes. And here's where the story gets both humbling and exhilarating. The universe is vast beyond human comprehension. There are hundreds of billions of stars in our galaxy alone, and most of those stars likely have planetary systems with their own comets and asteroids. The chemistry, the dynamics, the formation processes in those distant systems will vary. Some will be similar to ours, others radically different. Every interstellar object that passes through our solar system is a messenger from that vast diversity, a sample of cosmic processes occurring in realms we may never visit. When we study 3I Atlas, we're not just analysing one comet. We're glimpsing the broader universe, learning how planetary systems form and evolve in different contexts, testing whether our theories of physics and chemistry hold true beyond our local experience. The interstellar difference also raises tantalising questions about the future. If 3I Atlas is behaving strangely because of its alien origin, then what will we learn from the next interstellar visitor, and the one after that, Every object will be different, shaped by its own unique history and composition. Over time, as we detect and study more of these wanderers, we'll build a library of interstellar properties, a catalogue of how objects from different stellar environments behave. That knowledge will inform our understanding of planet formation throughout the galaxy, will help us interpret observations of distant protoplanetary disks, and will prepare us for the day when we might visit another star system and encounter its comets and asteroids firsthand. But there's a poignant element to this as well. Interstellar objects like 3I Atlas are fleeting visitors. They pass through our solar system once on their hyperbolic trajectories and then depart, returning to the vast spaces between stars. We have a limited window to study them, to learn everything we can before they're gone forever. That urgency lends intensity to the observations, to the analysis, to the race to answer questions before the opportunity vanishes. Every day that 3I Atlas is within range of our telescopes is precious. Every spectrum, every image, every measurement is irreplaceable data about an object we'll never see again. And perhaps that's fitting. The universe is full of fleeting wonders, of phenomena that appear briefly and then vanish, of opportunities that must be seized or lost forever. 3I Atlas is a reminder that cosmic exploration is not just about patient systematic study of stable, predictable objects. It's also about responding to the unexpected, about adapting quickly when something new and strange appears, about making the most of brief moments of discovery. The interstellar difference makes this comet precious, makes its mysteries more profound, and makes the urgency of solving those mysteries all the more acute. Because once it's gone, once it returns to the darkness between stars, we'll be left with only our observations, our data, and the nagging question of whether we asked all the right questions while we had the chance. And speaking of questions, there's one that's been lurking in the background of this entire discussion, one that makes people uncomfortable but can't be ignored. Why aren't space agencies being more forthcoming about what they're seeing, and what does that silence might mean? There's a conversation happening in academic circles, in astronomy departments, and in online communities that deserves attention, and it centres on a simple but provocative question. Why do the official statements from major space agencies about 3I Atlas feel so measured, so cautious, so limited in detail compared to the apparent significance of the observations? This isn't about conspiracy theories or accusations of cover-ups. This is about understanding the gap between what scientists are privately discussing, what limited information is being shared through academic channels, and what the public is hearing from official sources. And that gap is noticeable enough to warrant examination. Let's start with the reality of how scientific institutions operate, because context matters. Space agencies and major observatories are extremely careful about public communications, especially regarding observations that are still being analysed and interpreted. There are good reasons for this caution. Scientific results need to be peer-reviewed before they are announced publicly. Preliminary observations might turn out to be artifacts or errors. Interpretations that seem compelling at first glance might not hold up under scrutiny. The scientific community has a responsibility to avoid causing unnecessary alarm or spreading misinformation, and that responsibility necessitates a deliberate, methodical approach to public disclosure. That said, there's a difference between appropriate scientific caution and what appears to be deliberate vagueness. In the case of 3I Atlas, official statements have acknowledged that the comet is being observed and that it shows interesting characteristics, but they've been notably sparse on details about the Coma expansion rate, the specific nature of the thermal anomalies, or the implications of what's being seen. Press releases use phrases like unexpected activity or unusual characteristics without quantifying what that means. Journalists asking for specifics are often referred to upcoming papers or told that analysis is ongoing. And while it's true that analysis is ongoing, that's always true in science. The question is whether the level of caution is proportional to the uncertainty, or whether there's something more at play. One interpretation, and this is the charitable one that probably comes closest to the truth, is that researchers are genuinely baffled and don't want to make claims they can't back up. When data doesn't fit existing models, when observations defy expectations, scientists naturally become more cautious about interpretation. They don't want to be wrong publicly, don't want to propose explanations that later turn out to be embarrassingly off base. So they retreat into careful language, into qualifiers and hedges, into statements that are technically accurate but reveal little. From this perspective, the limited public disclosure isn't about hiding anything. It's about intellectual humility in the face of genuinely puzzling data. But there's another layer to consider, and it has to do with the nature of what's being observed. If the thermal anomalies and Coma expansion are as significant as they appear, if they genuinely challenge our understanding of cometary physics, then the implications extend beyond just 3I Atlas. They touch on fundamental questions about how matter behaves in deep space, about the diversity of objects in the universe, about whether our theories of comet formation and evolution need revision. Those are big claims, and big claims require strong evidence. Researchers might be holding back on detailed public statements, not because the observations are uncertain, but because they're still working out what those observations mean for the broader theoretical framework. They're building a case, marshalling evidence, preparing arguments that can withstand peer review, and until that process is complete, there's a reluctance to speculate publicly. There's also a practical consideration involving observing time and competition. Astronomy is intensely competitive. Telescope time is precious and hard to obtain. Research teams that are studying 3I Atlas have invested significant effort into securing observations, analysing data, and developing interpretations. They have a professional interest in publishing their findings before competitors do, in being the first to put certain pieces of the puzzle together. This competitive environment can lead to secrecy, to researchers keeping their best results close to the chest until they're ready to publish. It's not malicious or conspiratorial. It's the reality of how academic careers are built and how scientific priority works. But it does mean that cutting-edge observations might not be shared widely until they appear in journal articles, which can be months or years after the data is collected. Now here's where things get more speculative, and it's important to label this as such. Some observers have noted that when truly mundane or easily explained cometary phenomena are observed, space agencies tend to be quite forthcoming with details. Press releases are enthusiastic, data is shared relatively quickly, and scientists are available for interviews. The comparative reticence around 3I Atlas's most puzzling features has led some to wonder whether there's a reluctance to discuss observations that don't have neat explanations, that might fuel speculation, or that could be misinterpreted by the public. In other words, are agencies being cautious not because the data is uncertain, but because they're uncertain how to frame it for public consumption without triggering unwarranted excitement or concern? This touches on a deeper tension in science communication. On one hand, there's a desire to share discoveries with the public, to inspire interest in science, to justify the public funding that supports space research. On the other hand, there's a wariness about phenomena that might be sensationalized, that could be misrepresented in headlines, or that might lead to pseudo-scientific speculation. Interstellar objects are particularly sensitive in this regard because they automatically capture public imagination, and because any unusual characteristics can quickly be spun into narratives about alien artifacts or other exotic scenarios. The scientific community remembers the media frenzy around Oumuamua and the proposal that it might be an alien spacecraft. That experience likely influences how carefully subsequent interstellar objects are discussed. But let's be clear about what we do and don't know. We know that 3I Atlas is exhibiting a Coma expansion that appears unprecedented in scale and rapidity. We know that thermal observations show patterns that don't match standard cometary models. We know that multiple research teams are actively observing and analysing this object. What we don't know with certainty is why official statements have been relatively sparse on details. We can speculate about scientific caution, competitive pressures, communication strategy, or genuine bafflement, but without insider access to the decision-making processes at space agencies and observatories, we're inferring motives from limited information. It's also worth noting that the absence of detailed official statements doesn't mean the information isn't getting out. Academic papers are being prepared and will be published. Astronomers give talks at conferences where they share preliminary findings with colleagues. Some researchers are active on social media or give interviews where they discuss their work in more detail than official press releases do. The information is flowing, just through channels that might not reach the general public immediately or directly. For those willing to dig into preprint servers, watch conference presentations, or follow astronomers on social platforms, there's actually quite a bit of information available. The perception of secrecy might be more about the lag between observation and formal publication than about any deliberate withholding. But perception matters, and there's a valid argument that space agencies could do better at communicating uncertainty and ongoing investigation to the public. There's a middle ground between saying nothing detailed and claiming definitive answers. It's possible to explain to the public that observations are puzzling, that multiple hypotheses are being considered, that more data is needed, without either over-promising conclusions or being so vague that people fill in the blanks with speculation. Science communication has evolved a lot in recent years, and there's a growing recognition that the public can handle nuance, can appreciate mystery, and can understand that science is a process of investigation rather than a collection of settled facts. The situation with 3i Atlas is a test case for that evolving approach. Can agencies and researchers find ways to share the excitement and challenge of genuinely puzzling observations while maintaining scientific rigor? Can they engage the public in the process of discovery rather than just announcing final results? Can they acknowledge when something is weird and unexplained without either downplaying its significance or hyping it into something it's not? These are not easy balances to strike, but they're important for maintaining public trust in science and for fostering a culture where cosmic mysteries are seen as opportunities for learning rather than threats to be managed. And there's one more consideration that's worth mentioning. The scientists studying 3i Atlas are human beings, and human beings are complex. They experience excitement, confusion, doubt, and wonder just like anyone else. When confronted with data that doesn't make sense, their first instinct isn't always to broadcast that confusion. It's to sit with it, to work through it, to test and retest their assumptions before saying anything publicly. That's not deception or secrecy. It's professionalism mixed with very human uncertainty. They want to understand what they're seeing before they try to explain it to others. And in the meantime, while analysis continues and debates unfold in research groups and email chains, the public waits, notices the silence, and wonders what's not being said. The truth is probably some combination of all these factors. Appropriate scientific caution, competitive pressure, communication strategy, genuine bafflement, and the human desire to understand before speaking. None of that is sinister, but all of it contributes to a situation where the gap between what's known within the scientific community and what's communicated to the public feels wider than it perhaps needs to be. And as that gap persists, as more time passes with limited detailed disclosure, the questions multiply. What exactly are the thermal readings showing? How fast is the Coma actually expanding in real time? What are the leading theories that researchers are debating behind closed doors? And perhaps most intriguingly, what role does the comet's interstellar origin play in the cautious handling of these observations? These questions lead naturally into the realm of speculative science, where possibilities outnumber certainties and where imagination meets physics at the edges of our understanding. Let's step into territory where facts give way to possibilities, where observation meets imagination, and where the boundary between what we know and what we wonder becomes deliberately blurred. This is the realm of speculative science, where researchers put forward ideas that aren't yet proven, where models are built on assumptions that might or might not hold true, and where the goal is not to claim truth, but to explore possibility. In the case of 3i Atlas, that speculative space is particularly rich because the observations are so puzzling, and because the comet's interstellar origin gives us permission to imagine scenarios that might seem outlandish for local objects. Let's revisit cryovolcanism, but now with a speculative lens. We've discussed the possibility that subsurface volatiles might be erupting from within the nucleus, driven by internal pressure or heat. But what if the scale or nature of that activity is unlike anything we've seen in the solar system? What if 3i Atlas isn't experiencing the gentle plumes of Enceladus, but something more violent, more energetic? Some speculative models suggest that if an interstellar comet contains significant amounts of highly volatile ices like carbon monoxide, nitrogen, or methane, trapped beneath a surface crust, the sublimation of those ices as the comet warms could build up tremendous pressure. When that pressure exceeds the strength of the overlying material, you get a sudden explosive release, a cryovolcanic eruption that could inject massive amounts of material into the Coma all at once. This would create exactly the kind of rapid, symmetric expansion we're observing. This scenario is plausible from a physics standpoint, but it requires specific conditions. The nucleus would need to have a layered structure with volatile material trapped beneath a relatively impermeable crust. The warming would need to penetrate deep enough to sublimate those trapped volatiles, and the pressure would need to build to critical levels without finding easier pathways to escape. All of these conditions could exist, but we have no direct evidence that they do. This is where speculation becomes useful, not as a claim of what's happening, but as a guide for what to look for. If cryovolcanic eruptions are occurring, we might expect to see discrete events, sudden brightening or increases in outgassing, possibly correlated with changes in thermal patterns. Sustained monitoring could reveal whether the activity is steady or episodic, which would help distinguish between different mechanisms. Another speculative avenue involves the internal structure of the nucleus in ways that go beyond simple models. What if 3I Atlas isn't a single solid body but a contact binary? Two distinct objects barely held together by their mutual gravity. Contact binaries are known in the asteroid population, and there's some evidence that comets can have bilobed structures as well. If 3I Atlas is a contact binary, the interaction between the two lobes, the way heat and stress are distributed across the contact region, could create unusual thermal patterns. Outgassing from the neck region where the lobes join might produce symmetric coma structures, and the complex rotation of a binary system could explain the ambiguous photometric observations. This is entirely speculative, but it's testable with the right observations. High-resolution imaging, if the comet comes close enough, could reveal a binary structure. Detailed rotation modelling could show whether the light curve is consistent with a bilobed shape. Then there's the question of composition, taken to a speculative extreme. What if the materials making up 3I Atlas are not just quantitatively different from solar system comets, but qualitatively different? What if the ices include compounds that are unstable or rare in our local environment, but common in the interstellar medium or around the specific star where this comet formed? Interstellar space is known to contain complex organic molecules, some of which are highly reactive or exist in excited energy states. If 3I Atlas incorporated such materials during its formation, their behavior as the comet warms might be unpredictable. They might decompose, releasing energy and additional volatiles. They might undergo chemical reactions with other components of the nucleus. They might sublimate at unexpected temperatures or produce unusual spectral signatures. Some of the more adventurous speculative models even consider the possibility of exotic chemistry or physics. Could there be materials within 3I Atlas that were processed by cosmic rays during its long interstellar journey, creating compounds that don't exist naturally in the solar system? Could there be amorphous ices in metastable states that are only now transitioning to more stable configurations, releasing stored energy in the process? Could the extreme cold of interstellar space have allowed quantum effects or surface chemistry that would be overwhelmed at the slightly warmer temperatures of the Kuiper belt? These ideas push the boundaries of what we consider likely, but they're not impossible. The universe is full of surprises, and interstellar objects give us access to regimes of temperature, radiation, and chemistry that don't exist in our backyard. But here's where we need to pump the brakes and be honest about what we're doing. Speculation is a powerful tool in science. It generates hypotheses, it suggests observations, it pushes us to think beyond conventional models. But speculation is not evidence, and it's crucial to maintain that distinction. Right now, we have observations that are genuinely puzzling. We have a Coma expansion that's unusually rapid and symmetric. We have thermal patterns that don't fit simple models. Those are facts. What we don't have are definitive explanations. All of the ideas discussed above, cryovolcanism, binary structure, exotic composition, these are possibilities, not conclusions. They're consistent with some aspects of the data, but none of them are proven. And some might be ruled out with additional observations. The internet loves speculation, and in the case of unusual astronomical phenomena, that speculation can quickly veer into territory that's more fiction than science. There are claims circulating online that 3I Atlas is exhibiting signs of intelligent control, that the thermal patterns might be artificial, that the Coma expansion could be deliberate rather than natural. These claims are not supported by any credible evidence. They rest on misunderstandings of the data, on the assumption that anything unusual must be extraordinary, and on a desire to inject mystery and drama into cosmic phenomena. While it's natural to wonder and to ask questions, it's important to ground those questions in physics and evidence rather than wishful thinking. The reality is that the universe is full of natural phenomena that seem extraordinary because we're not familiar with them yet. Before we understood lightning, it seemed supernatural. Before we understood plate tectonics, Earthquakes seemed random and inexplicable. Before we understood stellar evolution, the life cycle of stars was mysterious. Unusual observations from an interstellar comet don't require exotic explanations involving intelligence or unknown physics. They require patience, careful analysis, and a willingness to expand our models to account for conditions and compositions we haven't encountered before. That's the hard work of science, and it's ultimately more rewarding than jumping to conclusions. That said, there's value in openly discussing the range of possibilities, even the unlikely ones, as long as they're clearly labelled as speculative. It helps the public understand the scientific process, the way researchers think through problems, the questions they ask themselves. It also prepares us mentally for the possibility that the eventual explanation might be something we haven't thought of yet, something that requires us to revise our assumptions or develop new models. Science advances not just by confirming what we expect, but by discovering what we didn't anticipate. And 3I Atlas, with its baffling behaviour and alien origin, is precisely the kind of object that could deliver that unexpected lesson. As more data comes in, as researchers publish their analyses and debate competing models, the range of plausible explanations will narrow. Some of the speculative ideas currently being discussed will be ruled out. Others will gain support and become leading candidates, and it's entirely possible that the truth will turn out to be something that combines elements of multiple hypotheses or something that hasn't been seriously proposed yet. That uncertainty is uncomfortable, but it's also the essence of frontier science. We're exploring unknown territory, and by definition, we don't know what we'll find. For those of us following this story from outside the research community, the speculative phase is actually one of the most interesting. It's when possibilities are wide open, when imagination and physics dance together, when the mystery is at its deepest. Enjoy that uncertainty. Embrace the not knowing, ask questions, propose ideas, but also maintain a healthy skepticism, a willingness to change your mind when new evidence arrives, and a respect for the difference between interesting speculation and established fact. The scientists studying 3I Atlas are engaged in exactly that process. They're speculating, testing, revising, and slowly converging on understanding. And as they do, the speculative fog will lift, and we'll be left with something even more valuable than mystery. Knowledge, hard-won, and deeply satisfying about how the universe actually works. But in the meantime, while speculation still reigns, one question looms larger than all the others, one that ties together the expansion, the thermal anomalies, the rotation mysteries, and the interstellar origin into a single unsettling possibility. What do these observations actually mean, and why should they unsettle us? Let's confront the word that's been hovering around this entire discussion: puzzling. It's a strong word, deliberately chosen to convey that the thermal data from 3I Atlas isn't just scientifically interesting or puzzling, it's unsettling in a way that reaches beyond academic curiosity and touches something more primal. But why? What is it about heat patterns on a distant chunk of ice and rock that deserves to be called puzzling? The answer lies not in what the thermal data shows, but in what it implies about the limits of our understanding and the vast unknown territories that still exist in the universe we think we're beginning to comprehend. The thermal anomalies are puzzling because they represent a failure of prediction. Our models of cometary behaviour are built on centuries of observations, on fundamental physics that we trust implicitly, on mathematical frameworks that have been tested and validated countless times. When those models fail, when an object behaves in ways that our best theories can't explain, it shakes our confidence. It reminds us that despite all our sophistication, despite all our technology and knowledge, we're still capable of being completely blindsided by nature. That realization is humbling, and humility in the face of the cosmos carries with it an edge of fear. Think about what the thermal readings actually represent. They're telling us that heat is distributed across 3I Atlas's nucleus in patterns that shouldn't exist given our understanding of how solar radiation interacts with icy bodies. Heat is going where it shouldn't go, it's persisting where it should dissipate, it's appearing in regions that should be cold. Each of these observations, individually, might have a mundane explanation, but together they paint a picture of an object that's thermally active in ways we don't understand. And when we don't understand something as fundamental as heat transfer, when basic thermodynamics seems to be violated or at least behaving in unexpected ways, it raises the disturbing question: What else about this object are we getting wrong? The puzzling aspect isn't that 3I Atlas is dangerous in any practical sense. It's not on a collision course with Earth. It's not emitting harmful radiation. It's not doing anything that poses a threat to our planet or civilization. The terror is intellectual and existential. It's the terror of confronting our own ignorance, of realizing that the universe is stranger than we thought, that interstellar space harbors objects and phenomena that don't play by the rules we've derived from our local experience. It's the terror that comes from expanding your understanding of what's possible and realizing that the space of possibilities is far larger than you imagined. There's also a visceral element to thermal anomalies that triggers intuitive unease. Heat means energy. Energy means activity. Activity in an object that should be cold and inert, an ancient frozen relic drifting through space, suggests that something is happening inside, something dynamic and ongoing. Our primate brains, evolved to notice signs of life and potential threats, can't help but react to evidence of unexpected activity. Even though we know intellectually that cryovolcanic processes or crystallization of amorphous ice are perfectly natural phenomena, the gut-level response to an object that's heating up from within, that's exhibiting thermal patterns suggesting internal processes, carries an echo of ancient wariness about the unknown. But let's ground this in specifics, because vague unease isn't scientifically useful. What do the thermal anomalies actually tell us that's significant? First, they tell us that our inventory of cometary behaviours is incomplete. We thought we understood how comets work, but clearly there are modes of activity, types of internal processes, or compositional regimes that we haven't accounted for. That's valuable information. It means we need to expand our models, consider a wider range of possibilities, and be more cautious about assuming that local observations generalize to the entire universe. Second, the thermal data tells us that 3I Atlas is actively evolving right now, during the time we're observing it. This isn't a static object we're cataloguing. It's a dynamic system undergoing changes, and we have a front row seat to those changes. That's scientifically precious and adds urgency to the observation campaign. Third, and perhaps most significantly, the thermal anomalies suggest that interstellar objects might be systematically different from solar system objects in ways we haven't fully appreciated. If the unusual behaviour of 3I Atlas stems from its alien origin, from the conditions under which it formed, or the experiences it had during its interstellar journey, then we should expect other interstellar visitors to also show unexpected characteristics. Each one will teach us something new, will challenge our assumptions in different ways. The universe is not uniform. Planetary systems form under diverse conditions, and the objects they produce reflect that diversity. We're only just beginning to sample that diversity through interstellar interlopers, and what we're learning is that we have a lot to learn. There's a philosophical dimension here as well. The thermal anomalies of 3I Atlas are a reminder that the universe doesn't owe us comprehensibility. It doesn't arrange itself for our convenience or limit itself to phenomena we're capable of understanding with our current knowledge. The cosmos is under no obligation to be explicable, and when we encounter something that resists explanation, that challenges our frameworks, the appropriate response isn't frustration, but wonder mixed with determination. This is what drives science forward. The encounter with the inexplicable and the refusal to accept that it must remain so. From a practical standpoint, the puzzling truth behind the thermal data is that it's forcing a reckoning with our assumptions about interstellar space and the objects that traverse it. For decades, we've theorized about what interstellar comets might be like, but theory is different from observation. Now that we have actual interstellar objects to study, now that we're collecting real data rather than speculating, we're finding that reality is more complex than our theories predicted. That's always the case in science. Theory gets you close, but nature has details and subtleties that only reveal themselves through observation. The thermal anomalies are some of those details, and they're telling us that our theories need refinement. But there's also an element of awe in this terror, and that's important to acknowledge. Yes, it's unsettling to confront the limits of our knowledge. Yes, it's humbling to be confronted with phenomena we don't understand, but it's also thrilling, it's exhilarating. We're living in a time when interstellar objects are passing through our solar system, and we have the technology to study them. We're witnessing cosmic mysteries unfold in real time. We're part of the generation that's expanding human knowledge into truly alien territory, that's learning about the universe beyond our solar neighbourhood, not through theory alone, but through direct observation. That's an extraordinary privilege, and the fact that it comes with puzzlement and uncertainty doesn't diminish its value. If anything, it enhances it. The thermal data of 3I Atlas is puzzling in the best possible way. It's a reminder that the universe is vast, strange, and full of wonders we haven't yet discovered. It's a call to humility, to curiosity, to the recognition that every answer opens new questions, and it's an invitation to embrace the unknown not with fear, but with excitement, to see mystery not as a threat but as an opportunity. Because at the end of the day, the most puzzling possibility isn't that 3I Atlas shows unusual thermal patterns. It's that we might live in a universe so predictable, so thoroughly understood, that there are no more mysteries left to solve, no more frontiers to explore, no more moments where data from a distant comet makes us question everything we thought we knew. The fact that we're not in that universe, the fact that mysteries still abound and that objects like 3I Atlas can still surprise us, that's something to celebrate even as it unsettles. And now, having journeyed through the data, the speculation, the mystery, the question becomes, what does all of this mean for us, for humanity, for our place in a cosmos that's proving to be stranger and more diverse than we ever imagined? So here we are, at the end of this journey through one of the most perplexing cosmic mysteries of our time, and the question hanging in the air is simple but profound. What does all of this mean for us? Not for astronomers or astrophysicists, not for space agencies or research institutions, but for you and me, for humanity as a whole, for a species that's learning to look beyond its own planet and grapple with the reality of an unimaginably vast and diverse universe. The story of 3I Atlas and its baffling behaviour isn't just about one comet. It's a chapter in a much larger story about who we are and what we're capable of understanding. First and most immediately, this mystery reminds us that the universe still has the power to surprise us. In an age where information seems instantly available, where we can look up answers to almost any question, where technology has mapped the genome and photographed distant galaxies, it's easy to fall into the trap of thinking we've got things figured out. Then an interstellar comet comes along and does something that defies every prediction. And we're confronted with the humbling truth that we're still beginners in the cosmic classroom. That reminder is valuable. It keeps us curious. It prevents the kind of intellectual arrogance that assumes our current models are complete. It keeps us asking questions and seeking answers. Second, the 3I Atlas mystery highlights the importance of sustained observation and scientific infrastructure. We're able to study this object, to track its Coma expansion and measure its thermal signatures, only because we've invested in telescopes, in detector technology, in the networks of researchers and institutions that make coordinated observation possible. Every image, every spectrum, every data point represents decades of development, innovation, and dedication. When we marvel at the mystery of this interstellar visitor, we should also marvel at the human achievement that allows us to study it. And we should recognize that continuing to explore these mysteries requires continued investment in science, in technology, in the education of the next generation of astronomers and planetary scientists. Third, this story is a powerful reminder of our place in a much larger cosmic context. We live on one planet orbiting one star in a galaxy of hundreds of billions of stars. Most of those stars have planetary systems. Many of those systems probably have comets, and occasionally those comets get ejected and wander through the galaxy, sometimes passing through our solar neighbourhood. Each one is a messenger from a distant place and time, carrying information about conditions, chemistry, and processes we can't directly observe. When we study 3I Atlas, we're not just learning about one object, we're sampling the diversity of the galaxy itself. We're learning that the universe doesn't produce just one type of comet, one type of planet, one type of chemistry. It produces endless variations, and every one we encounter expands our understanding. But beyond the big picture, beyond the philosophical implications, this mystery is also an invitation to engagement. You're part of this story. Your curiosity, your willingness to spend time learning about an interstellar comet's thermal anomalies and Coma expansion, your engagement with questions that don't have easy answers, all of that matters. Science isn't something that happens in isolation in laboratories and observatories. It's a collective human endeavour, and public interest, public support, public curiosity drive it forward. When you share a story about 3I Atlas, When you ask questions, when you express wonder about the universe, you're contributing to a culture that values exploration and understanding. So here's what I want you to do. If this mystery has captured your imagination, if you're as fascinated and unsettled by these observations as the scientists tracking this comet, let me know. Hit that like button, not just as a formality, but as a statement that you care about these cosmic mysteries, that you want to be part of the conversation as this story unfolds. Drop a comment and share your thoughts. What explanation makes the most sense to you? What questions do you wish researchers would pursue? Are you excited, concerned, curious, or all of the above? Your perspective matters, and this community is richer when we share ideas and wonder together. And make absolutely certain you're subscribed with notifications turned on, because this story is far from over. 3I Atlas is still being observed. New data is coming in. Researchers are working on papers that will provide more detail, more analysis, more insight into what's actually happening. As those findings are released, as the mystery deepens or begins to resolve, we'll be here breaking it down, exploring every angle, and following wherever the evidence leads. You don't want to miss the next chapter of this cosmic detective story. But more than that, think about what other mysteries might be out there waiting for discovery. 3. Atlas won't be the last interstellar visitor. There will be more, and each one will have its own story, its own unique characteristics, its own lessons to teach. We're living at the dawn of an era where interstellar objects are transitioning from theoretical possibilities to observable realities. The detection technology is getting better. The observation networks are expanding. We're going to see more of these visitors, and each one will be an opportunity to learn something we didn't know before. And finally, take a moment to appreciate the sheer wonder of this situation. Right now, at this very moment, an object that formed around another star, that drifted through the cold darkness between stars for perhaps millions of years, is close enough to our solar system that we can point telescopes at it and study its behavior in detail. We're watching it evolve, seeing its coma expand, measuring its thermal emissions, and puzzling over what it all means. That's not science fiction. That's happening right now. That's the world we live in, and you're here, learning about it, thinking about it, being part of the collective human effort to understand our cosmic environment. So yes, the thermal data is puzzling in its implications for how much we still don't know. Yes, the Coma expansion challenges our models and forces us to rethink assumptions. Yes, there's mystery and uncertainty and questions that might take years to answer. But beneath all of that is something profoundly hopeful and inspiring. We're a species that looks at a distant speck of light, that measures its heat from across millions of kilometers, that asks why its behavior doesn't match predictions, and that works tirelessly to find answers. We're driven by curiosity, by the need to understand, by the refusal to accept that the universe must remain mysterious. That drive, that curiosity, that determination to explore and understand despite the challenges, that's what makes us human. That's what makes stories like 3I Atlas's thermal mystery not just scientifically important, but deeply, fundamentally meaningful. And that's why we'll keep watching, keep wondering, and keep pushing forward into the unknown, one observation at a time.